Hi there, my name is Christopher Worst and welcome to the final video for Homework 5 for Transport 1. This will be going over Part 3, which asks us to derive the expression for heat transfer rate Q in terms of the overall heat transfer coefficient U, area available for heat exchange A, and the log mean temperature difference for a co-current heat exchanger. It also asks us to explain why this is also valid for countercurrent heat exchangers. So, we have, to start, we're going to draw a picture and then get to derivate. So, to start, we're going to draw a few pictures. We have concurrent pipes. My marker is starting to run dry. Let's change markers. Tactical reload. And my marker's got to fall off the table. That's okay. Have a tactical reload. Let's go for red this time. Oh, it didn't fall off the table. Okay. We have. Does that show up? Let's see. Yes, it does. Shows up well. Okay. So we have a hot current, we'll call that CH, and a cold current, call that CC. We have some temperature, hot temperature going in. We have some cold temperature going in. We then have a space here where the heat is taken from the hot water or the hot liquid to the cold liquid. And then we go to hot temperature plus the change in the hot temperature. And this also goes to cold temperature plus the change in cold temperature. Just to give a bit of a graphical representation, this is in general what this type of thing eventually looks like. We have here temperature, hot initial, an initial hot temperature, and initial cold temperature. Whoops, that's. We then have a final hot temperature, called that TH0, and then a final cold temperature. As you can see, these temperatures start slowly becoming more and more similar until eventually they just stop changing. They reach a steady state that is, in fact, not together because heat flow is not perfect in this scenario, but very, very close and close enough that heat doesn't transfer anymore. So we also have a area here, dA, and then we have in the middle here a shaded area, dQ. We have dQ up there as well. So we're going to start by writing out some equations for Q, this heat flow in both the hot, the cold, and overall. So we have a hot, cold, and then overall. So hot, the change in heat, this dQ here, is equal to the inverse, the mass flow rate of the hot liquid, multiplied by the heat capacity, Cp, multiplied by the change in temperature. This is also equal to the hot current CH, delta T, or not delta T, getting ahead of myself, this change in the hot temperature. We can do the same for cold, which is very, very similar. It's equal to the positive this time, mass flow rate of the cold liquid, multiplied by the heat capacity of the cold liquid, multiplied by the change in temperature of the cold liquid, which is equal to the cold current times the change in cold temperature. Now, overall, dQ is equal to the change in heat is equal to this heat transfer constant U multiplied by the change in temperature, delta T, multiplied by the change in area, dA. Now, take a little side tangent over here. Delta T is equal to the temperature, or the change in temperature of the hot minus the change in temperature, or not just the temperature of the hot liquid, pH, minus temperature of the cold liquid. Change in delta T over time is equal to a change in TH, the hot liquid, over time minus the change in the cold liquid over time. Now, the change in a liquid's temperature is equal to, not with regards to it, this change in the hot temperature, dTH, is equal to the inverse of this heat transfer coefficient, or this differential heat transfer, dQ, or no. This change in heat dQ divided by this hot current. We also know that by the same logic, the change in cold temperature is equal to the positive change in heat divided by the cold current. So we can substitute that in here. To say that the change in delta T is equal to dQ 1 over negative dQ, the hot minus plus the cold current. Now we know that dQ is equal to the heat transfer coefficient times delta T times the area, the change in area, over 1 over hot current plus 1 over cold current. Now, we have two scenarios here, scenario 1, scenario 2, initial scenario, final scenario, but that means that we can integrate. So we're going to give some squiggles from 1 to 2 of this change in temperature divided by the change in temperature, because we have that over here, is equal to the negative heat transfer coefficient 1 over hot current plus 1 over cold current times the integral from 1 to 2 of the changing area. That just goes to the natural log of delta T at state 2 divided by the natural log of, divided by the natural state, the average, the change in temperature at state 1, there, the difference in temperature at state 1, is equal to negative heat transfer coefficient multiplied by the area times 1 over hot current plus 1 over cold current. So we have this here, and I want to get to Q and the natural, or the log mean. We have area. So, taking these two equations from earlier, if we integrate this from states 1 to 2 or from states initial to final, we can say that Q, for hot, is equal to hot current times the temperature hot initial minus temperature hot at the end, and then cold will actually be the inverse. Q is equal to cold current times T at the final temperature minus the initial temperature. So that means that hot current is equal to Q over the difference in temperatures of the hot from initial to final, and the cold current is equal to the heat divided by difference in cold temperatures from initial to final. So we have this here, we can substitute it in here. So we have the natural log of the difference in temperatures at state 1 divided by the difference in temperatures, or difference in temperatures at state 2 divided by the difference in temperatures at state 1 is equal to the negative heat transfer coefficient times the area multiplied by 1 over Q divided by THI minus THO plus 1 over the temperature at the cold temperature at the final minus total cold temperature at the initial. Oops, Q divided by, there we go. Which then goes to the natural log of the difference in temperatures at state 2 divided by the difference in temperatures at state 1 is equal to the negative heat transfer coefficient multiplied by the area multiplied by THI minus THO divided by Q plus TCO minus TCI divided by Q. We can combine these two and then also flip them around, kind of maneuver them to get rid of this negative, to say that natural log of delta T2 over delta T1 is equal to UA over Q multiplied by minus, yes, THI plus TCI plus TH final position plus T cold final position. All divided by Q. Or actually, no. We want the inverse of that. So minus, minus, minus. And we actually have here, this is actually delta T no. HI, yeah, minus HO, then CO, CI. Here is delta T at temperature 2 minus change of temperature at state 1, which means that the natural log of delta T at state 2 divided by the temperature difference at state 1 is equal to the negative heat transfer coefficient times the area, delta T2 minus delta T1 over Q. We want Q in terms of everything else, so we can say that Q is equal to this heat transfer coefficient multiplied by A, which is a negative, divided by the natural log of delta of the difference in temperatures at state 2 divided by the difference in temperatures at state 1, which is then divided by difference in temperatures at state 2 minus temperatures at state 1, which this is the log mean difference of temperatures. So LMDT. But this is actually a legitimate mean, and I won't do the derivation, but basically as the numbers, as this two temperature differences get smaller and smaller, or the difference between them gets smaller and smaller, eventually this whole mean becomes one of the numbers. So all told, that means we have our heat equation here. And now it's time to explain why that works for countercurrent as well. So the only difference between co-current and countercurrent heat exchangers is this direction of the cold liquid, usually water. In co-current, they're going the same direction. In countercurrent, they're going opposite directions. Nowhere in this equation does directions come into account. The only thing it might change would be the difference in temperatures at state 1 and state 2, and that is in this equation, but it's in the log mean and it still works. So because the direction doesn't matter, and the only thing the direction affects is the log mean, which accounts for that, and the differences aren't noticeable at all. This equation as well works for both co-current, same flow, and countercurrent, opposite flow heat exchangers. And with that, that is the final video of the Transport 1 series. Thank you very much for watching. I hope you have a wonderful day.